Yes, so welcome everybody to an international seminar Automorphic Forum. So today's speaker is Anke Pohl from the University of Bremen that will teach us about resonances of Schottky surfaces.
Yeah, so thanks a lot for the invitation. I really like it that we still have these online seminars, in particular when we are kind of faraway places to meet, even though kind of officially Corona is over, which I personally don't 100% believe, but nevertheless. So what I want to talk about is, as said, resonances of Schottky surfaces. And I will, of course, explain always in the title. But before I start, let me also introduce these co-authors. So the first one, Oscar Bandlow, he is a reader at Queen Mary University in London. He is more in the direction of analysis, thermodynamic formalism. He's educated as a physicist. Torben Schick is a former master student of mine. So when I was in Jena, he is now at an IT company, but he still contributes to this project here. Alex Weisse is a physicist by training and is now working as a physicist and mathematician at the Max Planck Institute in Bonn. So what I want to explain today is as soon as, I forgot something. I wanted to give you the slides in advance so that you can go back and forth and have them separately. I first need to produce this link. So just give me a second, please.
No problem.
I will just do it here. So I actually started to prepare it and then I forgot about that. I can do it this way faster. Yeah. Because I know there are a couple of pictures and sometimes these pictures load very slowly when they are broadcasted. So it might be actually better if you have the slides also kind of at home. Yep, and files. Yep. Yep. And nope. Another second, it didn't copy. No. Where is it? Stupid. Yep. Okay. Oh, it should work. No. That is strange. Maybe this way. Yes. So in the chat, there is a link to a Nextcloud, and there we have the slides. And I will be here and go to the next slide only. So what I want to explain is what these pictures here mean, how they come about, and also kind of on the side, what they will have to do with automorphic forms, even though automorphic forms are here a bit on the minor level. I'm a bit sorry about that, but there's a lot of research to be done in the direction of automorphic forms, which we haven't done yet, and maybe someone is interested in these. So in the title, it said resonances of Schottky surfaces, and later on, I will try to convince you that these are pictures of resonances. But first, let me explain what are Schottky surfaces. So a Schottky surface is a hyperbolic surface of, I would say, the easiest kind you can have, but it's complicated enough for our purposes. So it has infinite area and it's convex co-compact, which in more down to the ground terms means there are no parabolic elements, so no cusps, and there are also here no elliptic elements. So these are actual Riemannian surfaces. These are not proper orbifolds. Okay, if you prefer to think about these as hyperbolic surfaces, in the notion of having a quotient space of the upper half plane by a Fuchsian group, then your Fuchsian group is non-cofinite. It has no elliptic elements, so it's torsion-free, and it has also no parabolic elements, so no cusps. Here you see two figures of examples of Schottky surfaces, and they actually look all of them look similar to this. So there is a number of funnels. So these ends, maybe I can go there with my mouse, these ends here, which are open. So what you see as a boundary is not a boundary. This extends to infinity, and they might also have a higher genius, so a number of holes. It depends on which surface you look at. But essentially, they all look like this. So how they are formed in terms of a kind of production, there is a quite easy construction of these surfaces, and this goes like that. You decide how many generators you want to have in your Schottky surface. Let's call this G. Here you see the example G equals 2. And then you take 2G little balls. They all need to be distinct. The center, so I do this in the upper half plane model. The center is somewhere on the real line. Of course, you can put it to infinity, but we won't do this. It's just too complicated to draw. And they are all distinct from each other. So here in the upper picture, you see a situation with G equals 2, and I just pick these 4 balls here. And below, you also see a G equals 2 with 4 balls situation. Now you decide on which ball you want to pair which other. And here you see it in the label. So -1 and 1 is paired, and 2 and -2 is paired. Okay. So on the upper picture, we have a pairing which goes like the outer 2 and the inner 2. And on the lower picture, we have a cross situation. Okay, then you pick elements in acid 2R, which is mapping these boards to each other in the sense that they map the boundary of these boards, which are in the upper half plane, to each other, and then the arterial of the one ball into the interior of the other, and vice versa. So there's some flexibility in picking these generators, but essentially in the end, it doesn't matter which one you take, you will see the same phenomenon. Okay, and then what is here depicted in, I would call it violet. Maybe you would call it blue. It depends a bit on what your screen is showing you. This is a fundamental domain for the group generated by these generators, which you got by these construction algorithms. Okay, and you just glue these now together, and in the upper situation you would get this 3 funnel surface, and in the lower situation, because you have this crossing, you will get a GDS1 situation with 1 funnel. And of course you can do this with many more balls, then you would just get more complicated surfaces. Okay, what's a resonance? So what we all like to think about is the hyperbolic Laplacian, which is here called delta, and eigenvalues and eigenfunctions of the hyperbolic Laplacian, typically in A2 when we think about automorphic forms. Here, because we have Schottky surfaces, there are not too many A2 eigenfunctions. Actually, the spectrum is finite. So we will be a bit more flexible and consider also kind of generalized eigenfunctions. And what we mostly interested is not the eigenfunctions themselves, but the eigenvalues, or more precisely spectral parameters belonging to them. So what we look at is the resolvent of the hyperbolic Laplacian, which is written down here. And we split the eigenvalue into S times 1 minus S, so kind of in physical space. So we talk about spectral parameters, and then this resolvent has a meromorphic continuation to all of C, and the poles of this resolvent in the meromorphic continuation, this is what is called a resonance. There's quite some knowledge now about these resonances and quite some gaps in our knowledge, even though there's hard work been done and this is still ongoing, but also because it's infinite area, kind of people didn't look at these problems for too long now. So important information, for example, is the first resonance in terms of when you draw resonances in the plane of S, so real part S, imaginary part S, and then first means coming from the right. So the first resonance is real, and it's typically called delta, and delta is not by accident the Hausdorff dimension of the limit set of the Schottky group, which you look at. First, also, of course, that means there are no resonances right to delta. And there are, by the way, also no resonances on the imaginary line sitting at delta. So delta is really there kind of alone. What we are very used to is a while law when it comes to infinite or to compact hyperbolic surfaces. The while law is not known for infinite area surfaces, but a while type law is known, and this is proven by Guido Pinswoski. It's written down here. So it looks like the typical while law situation. So you put somewhere in an origin of a ball, and then you count in growing balls with the radius here is r, and the growth is going in terms of order of magnitude by r squared. The while law would have a constant, so it would be an asymptotic, but for infinite area surfaces, this is not known. We only know these asymptotics as an upper asymptotic and a lower asymptotic. So it's not clear what these constants here are and how they are related to each other. It's also really not clear, not even from numerics, if we can expect of these, if these constants are the same or if they are different. So this is just the state of art at the moment. The interest in resonances for us coming from number theory is in calculating, for example, spectral gap or resonance-free zones. There's quite a work done by Frederick Noor, and this work, so he shows spectral gap situations. He also shows that around this data, there is a resonance-free zone. This is, for example, used by Bourgain, Gambert, and Zarnack in their generalization of Selberg 316 theorem. There's more work by O'Winter, and there's at the moment there's coming quite some work into this direction, doing here at some parts some progress, and some other parts some progress. What is also what I found very interesting is that these kind of results also went into the Bourgain-Kantorowicz work on Zaremba's conjecture, which is initially a priori quite a different story here. So Borthwick, he is an analyst working in spectral theory, very much interested in hyperbolic surfaces. When he went to a conference in 2013, he wanted to draw, just for fun, some resonances of some Schottky surfaces, just for his talk in the conference, and he expected to see resonances kind of somewhere, not with a particular structure. But what came out of his numerics is that there are more structures to be expected. And these are one of the two pictures which he produced. So let me explain what you see. On the left-hand side, you see the Schottky surface, which is up here in the corner, where all these lengths are the same. So all funnels have the same width, whatever this means. Just here, it's highly symmetric situation. Then he drew the resonances, so the poles of the solvent, the S, in the S plane. So here you have real part S against imaginary part of S. And whenever there is a resonance, he just made in there a little blue dot. And what you see as lines here, actually a lot of discrete points next to each other, but because we need to draw it somehow, it looks like a line. And these are all resonances in that domain which is drawn here. And you see they do not equidistribute. There is definitely an additional structure in here that was highly unexpected. Here what you see, the next thing here on the right hand side, you see also a Schottky surface, so also the resonances of a Schottky surface of this type up here, but this time one of this funnel width is slightly longer. Okay, but also here you see a lot of structure which was highly unexpected. Something which I will address later on. Note that these pictures at the moment end as 0, but the set of resonances does not end there. It goes up to minus infinity for the real part. There is an issue with the numerics which is used behind that. So how did he do that? The numerical approach. It was quite a clever idea the way he does it. So let me go through this. So instead of working with the Schottky surfaces and the resolvent directly, he used the Selbig zeta function. So I suppose major parts of the audience knows much more about the Selbig zeta function than I do, but nevertheless, let me introduce it here again. So the Selbig zeta function comes by definition as an Euler product. So it's the first product which we have here is over the prime periodic geodesics on the Schottky surfaces which we consider. So prime here means we count length by 1, so minimal length of geodesics. The length of the geodesic gamma goes in here in the exponent. And then there is a second product of auxiliary nature going via k, essentially kind of trying to capture multiplicities of geodesics, and then it's an Euler product in the formulation. What we know is that the Selbig zeta function converges if the real part of S is sufficiently large, and sufficiently large here is again the famous delta, which is also the Hausdorff dimension and the first resonance. And the Selbig zeta function, because it's a Schottky surface, has a holomorphic extension to all of C. For more general surfaces, it would just have a meromorphic continuation, but here we do have a holomorphic extension. Of interest for us is the result by Patterson-Perry, telling us that the Selbig zeta function has a 0 if and only if this S is a resonance, or it's a so-called topological 0, and the topological zeros are at minus the non-negatives. So at 0, -1, -2, and so on. These are absolutely well understood. We do not have to care about that. So we can focus on the first part, saying resonances are essentially the zeros of the Selbig zeta function. So instead of calculating resonances by means of the resolvent, we can try to find the zeros of the Selbig zeta function. This if and only if is essentially if and only if there is a kind of a finite number of exceptions to that in terms of some S's have a different multiplicities as a 0 and as a resonance. I will not worry about that too much here. For all the pictures, it's absolutely fine. So there's also something else which I like to stress here. It's about kind of ideas used here. So when you think about the Selbig zeta function from a kind of higher point of view, what it is an object which is purely geometric. It just comes from the geometry of the surface, which you consider. It takes advantage of the length of geodesics. Resonances, by their definition, are spectral objects. So this theorem here from Patterson-Perry, which is kind of an extension of Selbig's theorem of the same nature for finite area surfaces, shows us that the dynamics of the surfaces and their spectral theory have quite some relations to each other. When you're coming from physics, you see that this is based on, well, it's very similar to saying there is a relation between classical mechanics, which would be the side with the geodesics, and quantum mechanics, which is the spectral side. And actually quite a lot of what we are doing here is based on this quantum classical correspondence principle from physics as a motivation in the background, that we're kind of sure that there's something to gain when we go to the geometric, the dynamical side of our surfaces. So what Borthwick was after is calculating zeros of the Selbig zeta function. So how did he do it? He used a presentation of the Selbig zeta function as a determinant of, so a so-called Fredholm determinant of a certain operator. So at the moment, just just let's just say there is an operator which we call ls, so it's a whole family of operators of which we can take a determinant. I will explain in a second how these operators come about. The advantage of that is that instead of trying to calculate the zeros of the Selbig zeta function directly, we can try to take advantage of these operators ls by either trying to find one eigenfunctions of these operators or by using functional analysis or some kind of serious evolution of these operators. So because this is a seminar on automorphic forms, let me kind of make here a little excursion or a little kind of remark on how automorphic forms here come in. So these operators, which are typically called transfer operators, I will come into that in a second. When we would have at this situation here a cofinite, so a finite area hyperbolic surface, I could honestly say that the one eigenfunctions of the transfer operator, if they are of sufficient regularity, are in bijection with Mascas forms or other automorphic functions. For infinite area Schottky surfaces, we have not proven that yet. We have proven this for Hackett triangle surfaces of infinite area, so very similar surfaces, but they do have a cusp. But I'm actually quite sure that this result would carry over also to Schottky surfaces. So at this point here, there is a open question of how can we use in this business automorphic forms or automorphic functions to maybe get even better results on zeros of the Selbig zeta function for what we try to do here. Okay. So these operators ls, they are typically called transfer operators. They come from discretizations of the geodesic flow on the surface, which you consider. So how do we do this? What we try to do is, instead of using the surface itself and trying to understand where geodesics on the surface sit at, we unfold the surface again in the fundamental domain, so the picture here on the right, and discretize our geodesics by only asking through which sequence of fundamental domains they run. So they initially are supposed to be in the original fundamental domain, which is here violet. And then when they exit the fundamental domain, they will go, for example, into the D minus one ball, where which also means that they are enter a next fundamental domain, which is S1, so the generator S1 of the original fundamental domain. And then you give this geodesic the code at that moment S1. And then you just repeat and repeat and repeat, so they come with a sequence of symbols, very similar to continued fraction expansion. What these transfer operators do is they ask for exactly essentially these sequences and translate it or get it translated from a discrete dynamical system on R. So instead of saying you with your geodesic you entered the ball D minus one, you can also say your geodesic is ending at the real part of the ball D minus one. So this interval which you have here sitting, oops, did something strange? Oh no, it's all fine. You have sitting here in the real, so this interval, and then you transport the whole situation back to the original fundamental domain. So you have to apply at that situation, for example, S1 minus 1. And then you do this repeatedly and repeatedly, like you would do, for example, with the Gauss map in the continued fraction map. You would just get a self map on the boundary. Okay, and this you can interpret, understand as a discrete version of the geodesic flow. And the transfer operator is taking this discrete dynamical system, so the self map, and asking for evolution of densities under this map. There's coming a formula in a second. The way you should think about this informally is that a transfer operator is a discrete version of the Laplace operator, the hyperbolic Laplace operator on your surface, where you always ask for spectral parameter S. So in this specific situation, our transfer operator looked like this. Oh, this is the wrong mouse. You can write it down as a 4x4 matrix. There are a couple of zeros here on the counter diagonal. It is acting on functions on the part of the boundaries which you actually want to work with. And because these parts decompose into connected components, you can also split the function into these 4 parts here. And then it's applying this map TORS, which is written down here, which looks like the action and the principal series representation of in the line model, and actually it is. Or you can also say it looks like the slash S action, which it also is. I just have as a tau S because for me it's easier to work with the right action than with the left action. Okay, so what you should see is there's an implicit formula for writing down these transfer operators. It doesn't look too horrible, but every entry in this matrix is an operator on itself. So let's go back to this equality which we had. So you have this matrix, which is actually infinite dimensional, but it looks like a 4x4 matrix. And you are allowed, because you work on nice spaces, to form a determinant. And with this determinant, you can now try to approximate the Seebeck zeta function as follows. So the first thing which you do is you use a power series expansion, because determinants, when it comes to these type of operators, are always defined as E2 log of this determinant, so it goes via the trace. So this is the formula which you need, and I included an additional Z to be able to show where it comes from. So we have a Z here, which in our Euler product goes here. This W gamma is the word length of the periodic geodesics in the symbol. Because it's periodic, it has a periodic coding sequence, and you just take the word length of that. Then it is the same as the Fredholm determinant of our transfer operators multiplied with this Z, which goes by essentially definition of Fredholm determinants or identities within Fredholm determinants into this formula of x to the minus the harmonic sums of the trace with the Zn in here. And this you can expand with the exponential power series again into something which looks like this, and this DNS, they just come about. They're just the coefficients which you have in here. Okay, so we have this formula, and in the end, we would like to use Z equals 1. What we know about this formula is that every single of these traces which we have of the powers of the transfer operator is formed by some elementary changes. So let me do something which I hate when speakers do it, but let me go back. So we had this 4x4 matrix of operators, and you can work, because everything is kind of very tame here, you can work with these operator valued matrices actually similar to standard matrices, standard 4x4 matrices in R. So you can just calculate a trace by using the trace here, and when you do a power, you just add up some of the components and multiply them, and you just do again the trace. So what goes into these traces is always traces of the single entries of these tiny operators TORS. So this is something which you have very much under control. Okay, and the dn's, which are the coefficients here, also these are coefficients you can effectively calculate via recursion when you know that you only need, let's say, the first 100, 1,000, and so on. There is a formula how to calculate that. The problem, which is a slight problem, is actually that it's a recursion formula. I will come to that. Okay, so the idea to calculate or to approximate the zeros of the Seebeck zeta function is to use this formula up here, put the Z back to 1 and just chop it off at a capital N, which is sufficient for the approximation which you would like to have. So instead of calculating zeros of the Selbig zeta function right on the nose, which is difficult numerically, you use this formula down here, which is a finite formula, and try to find the zeros here, which is still a slight problem, but it's much more compact, the problem. Okay, so how good are we in approximation here? So there is an approximation error estimate of the dn's, which is the important thing you need to have here, which is of course only an upper bound, but kind of the nature of the upper bound is the error which you actually have. So what you see here is this. All these little c's, so the C1, the C2, the C3, these are all positive numbers. As long as the real part of S is positive or 0, then, and the imaginary part is not too large, then you're actually quite fine. You can just turn the n up a bit and the error goes down. You remember that the pictures which Borthwick produced stopped at real part S equals 0. And there is a reason for that, because as soon as the real part of S is negative, then this minus in front of the C2 is effectively a plus. So you are adding something, which means the further you go into the negative real parts, the larger your error will be. Same for if your imaginary part goes up. You can try to compensate by that with enlarging the capital N, so using more and more approximation terms, which actually works for some time, because here it goes by square, so it's kind of killing a bit the additional problems you gain. But nevertheless, it's a bit limited in these terms to a domain. And this is something Borthwick also observed already back in his thing. Nevertheless, he produced these wonderful pictures there. So the next thing what we would like to try is to go more into the negative real parts, because this is where kind of the major life of the resonances takes place. Resonance is spread over all the negative real parts here. So how can we do this? There's a new idea then. We would like to get rid of too many calculations. So again, a step back. There are two things where calculation power goes in. This is calculating these traces, even though that is not too costly, and of course the recursion formulas, which means as soon as this capital N goes up here, you need to calculate more and more recursions. Recursions are dangerous when it comes to calculations. First, because there are many more terms, and the second part is, as soon as you have an error and you put in a numerical error and you have a numerical error in a recursion formula, it typically starts to propagate. So the idea here, originally coming from Chitanovic and Eckhart, was to use symmetry in the surfaces to try to calculate less numbers. This is something which was done by Borthwick and Weich. So what they did is they really kind of did a symmetry breaking. So they put in representations. They used all the symmetries which are in the spaces. They could bring down the number of necessary calculations so that they could go some part also into the negative domain here. And you see pictures go on here, and they could also go, oops. They also could go up with the imaginary part. So you see, before we had something like 1,000, 2,000, now we had 10,000. And you see pictures gain from that. They become nicer, you see more structures, you see that there's actually something to observe. So what we did, we said, okay, we want to have a completely different algorithm that doesn't use recursions at all. Because let me go back. What you see actually here is it becomes a bit fizzly at this part here. So this is where these calculations, they are very nice, But as soon as you go into the negative reals, you need to be very careful here that you do not accumulate too much numerical error. So we wanted to have something, a new algorithm where you do not have to deal with these numerical errors. And this is what came out of that. And as soon as we had this picture, we said, okay, that was worth the effort, because you see not only the old structures in here, but you see we do gain new structures here. It kind of opens up a door to a very nice new world here. So let me try to explain what we did. So as I said, we wanted to avoid these recursion formulas because of the problem of error propagation. And we also wanted to avoid these truncations, because as soon as you have a truncation algorithm, it means when you want to improve, you get more and more terms which you need to handle. But we also started with this formula up there, because that kind of from physics intuition is the thing you should do here, or at least which seems to be reasonable to do. What we took advantage of is that these operators have more structures than what was used before, namely they come with an integral kernel. So all you need to see here at the moment, so I wrote down the formulas for people who like formulas, but what you actually should see here, you can do this, you can write down the transfer operator as an integral. You have a kernel which you have in explicit terms. So whenever you give me your favorite Schottky groups, I would write down all the C, Ds and Ms and whatever. And this kernel is just a finite size matrix, and every entry is of this form down here. So it's not too inconvenient, or it's a zero, and there's actually quite a lot of zeros involved. Okay, so our idea was, instead of using a truncation and a power series expansion, we would do this via this kernel. So what we needed to do is to approximate now this integral with a kernel and then put it into our determinant formula. What we used is the Nyström method. I will come to that on the next slide. And what it comes down to is to use Gauss-Chebyshev quadrature formula, which is something you typically learn somewhere in your numerics classes and then start to forget about that. But we had to go back to that. So what does it mean for us? You can approximate this determinant here. So instead of the operator, the transfer operator itself, you essentially just have you put in the integral, and then you approximate the integral, so it becomes a finite expression in terms of the kernel, where you evaluate the kernel at specific points, because we use Chebyshev polynomials as a basis, which is very convenient here. We use, of course, the Chebyshev collocation points, which, for those who are interested in that, are these cosine values here. And note they are all just sitting on the interval, so we are not calculating on the upper half plane, we only calculate in R. Then there are certain weights which come out of the theory of approximation, and then it's an n by n matrix. And something I would like to stress here again already is the here down here, you again have the formula for the kernel. So every entry is of this form or is 0. If you now put in the x's, so the xi and the xj instead of z and w, and you see, okay, it goes to specific places. And then later on, we would like to change the value of s. So which means when you change the value of s, you can reuse quite a lot of the kernel which you already had calculated. You only need to exchange this little exponent here. So it means it saves you quite some computation time, because you can reuse larger parts of the values which you already have. And you also can do all your calculations in parallel, because every single entry of your kernel is calculated separately in parallel. Okay, so then instead of calculating the zeros of the Zelig zeta function, which we cannot, we want to have the zeros of this d. Okay, which is now a finite, an honestly finite size matrix. So that is, of course, complicated because the S here is in the exponent. Doing this kind of with real algebraic expressions seem to be impossible. So we calculated also these zeros here numerically. How did we do that? So we used Newton's method, and here's a kind of a picture version of why Newton methods works here quite well. So let me go first to these little pictures and explain what we see here. So in this picture up here, the tiny picture on the left-hand side, the top one, what you see is the map Z goes to Z, so identity, and the Z is presented as in the argument. So it's R times e to the minus phi, and we're drawing the phi in color. So red means phi is 0. Yellow is phi is, I don't know, p quarter or something like that. So it goes one time around the rainbow if phi goes from 0 to 2 pi. This slight darkness here, the saturation, this encodes the magnitude, so the absolute value. So you can ignore just that. Okay, what you see here is Z equals, Z goes to Z has 1 0 at 0. You discover a 0 by having one rainbow gone through, and then the point in the middle is your 0. Okay? The map, the picture 1 down is the map 1 goes to 1 over Z. So we have a pole at 0, and you see it also here in the picture. Now the rainbow is in the opposite order, so you go around 0 in the other direction when you follow the colors. So this is a pole. Okay. The next one is the map Z goes to Z squared. That has an order of 0 of order 2 at 0, and you also see it here again in the picture. You start at red, you go through the rainbow. You are at red again, you go again through the rainbow, so you turn around some point twice in kind of rainbow orientation, so it's a 0 of order 2. What you see in the capital pictures here, the big pictures here, is actual phase plots for the ds for specific surfaces. And for example, down here we see a first resonance, so a first 0, because here you see one rainbow. For example, here at that point, you see a 0 of order 3 because you have 3 rainbows. And so it goes. And the idea with the Newton method is now, because you cannot really pinpoint the zeros by numerical calculation, you calculate at some places where you are quite sure that you might start hitting zeros, so where you get some information of zeros. So for example, if you manage to hit, let's say, the green or the yellow part, and then you do a descent by following the yellow part until you're at the 0. Okay, and this is what Newton's method does. So here it is again. So this is a Schottky surface with one generator. Just for drawing pictures is much easier. This is the formula which you evaluate in Newton's method. So you start at some point as n, so as 0 actually, which you try to choose in a nice way. And then you try to find if there is a 0 already by essentially calculating differential quotients, and try to approximate more and more, or going more and more into the direction of a 0. And as soon as this kind of terminates, if you're stable at a point, you have your 0. So and here you see another feature which was also visible before. If you try to hit at anything else but red, you will be transported by Newton's method directly to a 0. And you can do that by, so if you try to calculate, let's say, resonances, so the zeros at some domain, let's say real part is larger than -5, you try to use the line -5, densely spaced with initial starting points, and then you will immediately be transported to larger real parts, because as an additional feature of the Selbig zeta function and also the approximating objects, all the non-red colors go to the left. So they always have the tail to the left. Okay, so here in the next picture you see which is called the Newton basin. So as soon as you, for example, here have a starting point in the red part, you will immediately be transported by Newton's method to the 0 here. When you start in the blue one, you will end up here. So it's a quite safe thing to do here. Newton's method also numerically is very easy to use. So the idea to use Newton's method and also this kernel approximation is nothing we invented from scratch. It's a method which has quite a long history. There is a survey article by Bornemann. It sometimes also goes in combination with other methods. This would be the Lagrange-Chebyshev approximation. But it's still used in many applications also today. It's used so this is where we got the idea from. This is used in applications in physics. So because two of my co-authors have a physics background, this is how it came about. And it's also used for other purposes in this business. So here I'm just giving you some names for that. What we contributed to this method for making it possible for the Schottky surfaces is one thing. Is a choice of good spaces on which we can work. So these operators LS, they need to be defined on good spaces, otherwise the whole thing does not work. Instead of using symmetry breaking by introducing some representations, we discovered that in this setup it's more efficient to do what we call adaptive domain refinement. So instead of working with a large boards initially and base the whole algorithm on these large domains, we would just go on a couple of refinement steps and do the whole thing on a smaller scale, which does contain the same information because there is a lot of kind of funnel space at the boundary. And what we also did is rigorous error estimates so that we can show that these algorithms are actually stable and they show what we see, what we think they see. This is not kind of some artifacts. So one word about the error estimates, and then I will come with a couple of pictures. There are two types of errors which you encounter. The one is the error which you get by going from the Selbig zeta function to the approximating object. So in our setup, going from the ZS to the DS, the determinant approximation at S. This is something I call as a pure math approximation. This has, when you turn up the number of Chebyshev polynomials in this business, has exponential convergence. This is something we proved. Methods are functional analysis, which goes in there. Then you have a second error, namely because you never can work, these are irrational numbers, which you typically have to handle. You can never work with irrational numbers in a computer, honestly, when it comes to numerics. So there's always a numerical error. But here we do have good conversions because calculations are independent of each other. There's just no error propagation. There's no recursion formulas involved. This is something which is also intensively discussed in the survey article by Bornemann. Bornemann, by the way, is a numerics professor in Munich. And there's, of course, then the errors which come from the Newton's methods, which we just kind of use as a black box here. But Newton's methods is known to have very good convergence, so there's no additional numerical problem in here. So now let me show a couple of pictures, what we can now observe and see, and where are open questions and so on. So of course we were quite proud on these results, and then tried to kind of squeeze out of it nice pictures, particularly going into the negative reals. Initially, we were not so interested in going with the imaginary part high up. So what you see here on the left, it is funneled surface. So this surface which you see down here, the resonances of those. You see initially which we had was the picture here at starting at 0, kind of in this part here. And you see when you can go further up and further to the left, you do see new structures. What we do not understand yet is a mathematical reason for these resonance-free poles. So if you have any idea how to do this, what they might mean, how to prove that they are there, where they are, what they mean, just let me know. I would be very interested in that. What you also slightly observe already in this picture is that it looks a bit like this. So there are these structures in the picture, and they seems to start at, when you try to trace them down to the real axis, they seem to start at the first resonance, which is here at dot 2, and then all the topological zeros. So this is 1, this is 0, this is -1, there's also -2, and so on. Because if you look deeply in the numerics, if you kind of zoom in here on the axis, these here, they do not seem to stop here at the axis. They seem to turn around and go to these integers and the first resonance. So on the right-hand side here, you see an enlarged picture, the 3 funnel surface. So here we before also had the part starting at the 0 to the right. And here you see, okay, there's much more structure to gain. One thing which I would like to ask you to think about for some parts, and then I will come back to the question, is if I show you the picture, so if I give you these two pictures, you would definitely say, okay, they are different, they have different features. And looking at the picture, would you expect to be able to determine if you have a funneled thing like this here, so with a hole, or you have a 3 funneled? So if you have a torus situation, or you have a only funneled situation. So I will come back to this question in a minute. So what we were asking ourselves as well is, what happens if I have more than 3 funnels? So this is always now the very symmetric situation. There is an heuristical argument in the literature saying that as soon as we have a number of funnels, so as soon as these surfaces become more and more complicated, we shouldn't expect too many structures anymore. This heuristics is based on two ideas. The one is numerical results, but the problem is the numerical results which existed for 4 funnels before that, which is for this little part down here. And of course, if you have only a little window of your situation, you cannot see too much. The other idea is that because you have many lengths, so many numbers in your formulas which are essentially irrational to each other, you shouldn't expect too many structures anymore when you try to combine them. But then we just tested first if this algorithm is able to do calculations for funnels and even more funnels, because there was a problem before in terms of numerical power, because algorithms were slower. And then, of course, we wanted to see, do we see structures? And then I must say, I mean, Claire knows this. I have a background in ergodic theory, and ergodic theory is never a good idea to look at small windows. You always try to look at this from far away, and this is what we did here. So as soon as you look from far away onto the situation, so meaning you have a bigger window, I think we all agree there are structures. So this conjecture is nothing we should keep. It's when you see more of the world, you do see it again, but you also see that it's kind of more stretched out, which is of course there because you have more information which needs to combine to each other. But also here you see something very nice. If this conjecture or this idea of that structures start at integers and the delta is okay, then here at the 0 you have a very good support to that conjecture. Okay, next picture. For funnels was never calculated before because algorithms just there were too many numbers to be handled. With this parallel algorithm, we can do that. And also here you see, yes, you do have these structures still. Here at some part we just didn't extend the pictures too far anymore. We had to stop somewhere in the computer. So here here word towards calculation power. So this is 6 funnels, which also worked still. And here I would like to show you in terms of pictures what means calculation. So we are calculating on a workstation with 16 cores, which is equivalent to 4 laptops. And here you see what we can do in 4 hours. It's a still desktop computer, so this is the computer which is in front of me. So you see algorithms are not too slow, which means within a week you have the full picture done, sometimes even in 2 days. Okay, next picture here, which is a big problem sometimes in this business, because when it comes to higher numbers or larger numbers, things become complicated. The question was, when you have your first resonance, large means above 1/2, can you still do something? And here, yes, you see it's still possible to calculate these. And it's also, just note this just goes up to 200 because we had to stop somewhere in calculation. So also here you still see these structures. There is a conjecture where the real parts of these resonances should accumulate. I'm not sure whom I have to attribute this conjecture to, but nevertheless, there is the conjecture, and it's quite a reasonable conjecture, that at delta half, you should see the first accumulation of resonances in terms of the real part of the resonance is accumulating there. Here's our data. This line delta half is, so here's the line of delta half, this straight line here. From the picture, it might be that, so the picture seems to support this conjecture. So let me say it that way. If you have larger pictures, it also seems to support it. This is all we can say here. Here's also something nice you see is at 1/2, this is this dashed line here, resonances cannot cross real part 1/2 unless they are delta. So delta is here. And you see, if you kind of take your fantasy, that data, that resonances try to come in from the left, and then they are kind of caught here at 1/2. This is proven that you cannot go beyond 1/2 here. So here's something else, which is something we don't know what to make out of that. So there are no proofs, but it's just an observation. So we had the pictures before of the torus funneled situation, so this here, and a purely funneled situation. And we took an overlay of the 4 funneled and the torus funnel situation. So the 4 funnel is the violet crosses, and the green dots is the torus situation. And you see, we can somehow, it seems that the one structure sees the other. It's not 100% on the nose, but you see that there are substructures which belong to each other. We did not prove anything about that. It's just an observation at the moment, but there's definitely some information to gain out of that. So one last picture here. There is this spectral gap proof. which shows this, which states this. Here, you have to turn your head around or just turn the picture in your head. So real part goes up here, and the imaginary part is the horizontal axis. So the what is proven is this. There is the first resonance data, which here is at this green line. And there is a small part, so there's a small kind of resonance-free zone about this data. And we try to, if we are able to observe this numerically. So, and then you try to think about this in terms of calculation during time. So you start calculating here near the real axis and think about the resonances, which you see from coming from time to time. So you would say here, oh yeah, this is good, this is good. Oh, it's going down. Here's a big, big gap, big, big gap. And then you say, ooh, oh, it's coming near to my axis again, near to my axis. And say, oh, it's going to be good, good, fine, we are fine, we are fine here. And then it comes up again and again. But you're still quite happy because in total, there's an envelope, so it goes back, it goes back, it goes back. Then you say, oh, we don't know, we are lost here. So you see, there is evidence, but not really here. So numerically, it's very hard to say what is really happening here. There seems to be kind of, how should I say, an uncertainty principle, kind of oscillation principle still of the resonances on smaller scale, so that because there is a proof, the large scale goes away from the axis. Also here, just one last word, the delta half axis is down here. The next line, which you see here, I'm not sure that one sees it on the screen, but you would see it in the file. Here is where it's supposed to be the first accumulation. And with this picture, we could say, yes, this is a conjecture which might be true. So that was the last picture here. So thanks a lot for your attention.
Thank you a lot. Thank you a lot for the nice talk. So let me stop the recording.